Hi everyone, welcome to this lecture about mixed strategies. In the previous lectures, we went over the basics of game theory. We looked at different strategies that are available to players. We looked at best responses analysis, the best strategy given the strategy of another player. We also then looked at the concept of a Nash equilibrium, where players are playing a best response to each other. So a Nash equilibrium could be defined as a mutual best responses. And then we went over some applications where sometimes strategies were continuous, like choosing an output level or price level, or strategies could be discrete. Let's say cooperate versus not cooperate, goof off versus work hard, confess versus not confess. In this lecture, we are going to go over the case where players can play some strategies, but they don't play a given strategy 100% of the time. The idea is that they are going to play in an unpredictable way by sometimes playing one strategy, sometimes playing another strategy. The usual disclaimer: I do not allow this content to be published without my consent. If I see it online, I will take it down and report whoever uploaded it. In the last lecture, we finished on the game called Matching Pennies, where you have a penny in your hand, your opponent has a penny in his hand. You both show a side of the penny at the same time. And the rules say that if both pennies match, you win and your opponent loses. And if pennies don't match, heads versus tails, for instance, then your opponent wins and you lose. We saw that in such a game, there was no Nash equilibrium in pure strategies. After doing the cell-by-cell inspection and underlying the payoffs, we found that there was no cell in the payoff matrix where both payoffs were underlined. This game is a constant sum game. In particular, it is a zero-sum game because whenever somebody wins one, the other loses one. So it's a game of pure conflict. Constant sum games are games where the sum of the payoffs is constant. Here, it always adds up to 0. So, in such a game, it is important for players not to play in a predictable way. If the strategy of your opponent can be predicted, then you can play the appropriate counter strategy and you will win. So, your opponent doesn't have an incentive to always play the same strategy. No Nash equilibrium in pure strategies. Now, if players randomize over their actions, we say that they play mixed strategies. A mixed strategy is one where a player plays some of the available pure strategies with certain probabilities. The concept is easier to understand when you think about repeated games where, for instance, you play matching penny with your friends many times in a row. Let's say 10, 20 times. Rock, paper, scissors. You could play in a best of 5 and so on. Where each player's aim is to keep the other guessing. So, rock, paper, scissors. Penalty kicks. When you have 5 penalty kicks in a row per team in a soccer game, for instance, then you do not want to always hit the same spot. Eventually, the goalie of the opponent's team is going to realize, oh, they always go on the right, so they always hit on the right, on my right, so I should duck on the right. Same for tennis point. If you always hit the ball back in the same spot, then your opponent can predict it and counter more easily. Tax audits. If you are a firm which is expected to file your taxes properly every month or over the month for value-added taxes, or every year to make your overall summary of your past year activity. Then, as an auditor, you do not want to let the firm know when you are going to audit them. An audit is pretty much a control. You're going to check if the numbers they enter in the payrolls, in the taxes, in the sales, and so on actually match. If the firm knows when the auditor is coming, then they can prepare the employees and make sure everything is very tidy before the audit happens. Same with drug testing, in particular in sports competitions. If, as an athlete, you know that you're going to be drug tested at a specific time, then you can stop taking some drugs in advance so that they will not detect anything in your either your blood or your urine. A mixed strategy Nash equilibrium is going to be a Nash equilibrium where at least one player randomizes over his or her actions. Note that you don't need both players to randomize their actions in this case. At least one of them should. Well, I say should, I mean, if at least one of them does, then it's going to be a mixed strategy Nash equilibrium. Some games only have mixed strategy Nash equilibria, like matching pennies. Others have Nash equilibria in both pure and mixed strategies. Chicken game, which we are going to go over today, or coordination games. Once you learn how to find the mixed strategy Nash equilibrium, go back to the coordination games we saw 2 lectures ago in the concept of Nash equilibrium, and you'll be able to find mixed strategy Nash equilibria as well. So, since we started talking about matching pennies, let's go over it again and let's look at how players can randomize over strategies. Randomize means you're going to play a strategy with a probability of, let's say, 30% and another strategy with a probability, let's say, 70%. Or you could flip a coin to decide what to play. 50% of the time you're going to play a certain strategy, 50% of the time you could play another. Note that you could randomize over more than 2 strategies. You could play one of them 30% of the time, the other 30% of the time, and the third strategy 40% of the time. Probabilities at the end of the day have to add up to 100%. So here's the process. First of all, put yourself in the shoes of Ro. I always start with Ro, it's just easier for me. Choose whatever you feel like. And I'm going to assume that the player Colin plays heads with probability P and plays tails with probability 1 minus P. So both probabilities add up. Now, if you put yourself in the shoes of Colin, you're going to do the same thing for Ro. You're going to assume that Ro plays heads with a probability Q, a different probability than for Colin. And 1 minus Q is the probability that Ro plays tails. Now, to find the best responses, given that the other player plays this randomized strategy, instead of computing the straight payoffs, we need to compute an expected payoff. An expected payoff is the same as the average payoff. Expected comes from expectation, which in probability and statistics means the average of a random variable. Since the strategy of your opponent now is random, because it's a mixed strategy, then your payoff will not only depend on whether he plays heads or tails, it will depend on both at the same time. So, we are going to compute the average payoff of Ro if he plays heads, when Colin plays with these P and 1 minus p probabilities. And same for tails. So here is the process, and this is how you should always solve for a mixed strategy Nash equilibrium. That's at least my advice. You can always do it another way, but this is the most systematic way, and it is relatively straightforward. So suppose Colin plays heads with probability p. If rho plays heads, then if you look at the matrix payoff, with probability p is going to get a payoff of 1, and with probability 1 minus p, he's going to get minus 1, because in this case Colin will play tails. So the expected payoff of rho is 1 times p, that is the case where Colin plays heads as well and he wins, minus 1 times 1 minus p, the case where Colin plays tails and then rho loses. Adding those things together and you get 2p minus 1. This is the expected payoff of rho if he plays heads when Colin plays heads with probability p and tails with probability 1 minus p. Now, if instead he decides to play tails, it's going to be the other way around. With probability p, he's going to lose and get minus 1. And with probability 1 minus p, he's going to win and get plus 1. So his final expected payoff in this case will be 1 minus 2p. And now I do the same thing for if I put myself in the shoes of Colin. So Colin is thinking rho plays heads with probability q. Sorry, that's a typo here. So if Colin plays heads with probability q, he loses because they both play heads. And with probability 1 minus q, he wins and he gets a payoff of 1. Adding them together and you get 1 minus 2q. Same, if Colin plays tails, he gets 1 times q minus 1 times 1 minus q. With probability q in this case, he wins. And with probability 1 minus q in this case, he loses and gets a payoff of minus 1. And that gives you 2q minus 1. So you can take the same payoff matrix as the previous slide, but now you can extend it. At the end here, you can add rho's expected payoff. So with probability p, he gets 1, and with probability 1 minus p, he gets minus 1. When you add those things together, you get this 2p minus 1, which you can report here. If he plays heads for sure, when Colin randomizes, he gets 2p minus 1. If he plays tails, and Colin randomizes, he gets 1 minus 2p. Same in the case of Colin. Colin's expected payoff, when he plays heads, and rho plays heads with probability q, his expected payoff will be 1 minus 2q. And minus 1 plus 2q if he plays tails. Note that the expected payoff of Colin depends on the probability of rho, and the expected payoff of rho depends on the probability of Colin, the probability of playing heads. Any questions so far? It is very important for you guys to understand what's going on here. Why it is added and subtracted. The minus here comes from the negative payoff. It comes from the minus 1. In principle, you should always add all the payoffs. But here, since we have negative payoffs, then sometimes we get minuses. Any other questions? So the first step of the process is to find the expected payoffs of each player when the other player plays randomly. Now, since we know the expected payoffs of Rho when he plays either heads or tails, we can compare them and see when he prefers to play heads or when he prefers to play tails. So, if 2p minus 1, this one here, is higher than 1 minus 2p, then Rho is better off playing heads. Heads gives him a higher expected payoff, which means on average, he will have a higher payoff by playing heads all the time than by playing tails all the time. And the other way around. If 2p minus 1 is lower than 1 minus 2p, then Rho prefers to play tails all the time as opposed to heads all the time. Note that if either of these inequalities is satisfied, then Rho doesn't want to randomize over his strategies. He wants to play either heads for sure or tails for sure. If they are equal, however, Rho is indifferent. If they are equal, it means that on average, if he plays heads all the time or tails all the time, it doesn't matter, on average, his payoff will be the same. So, he could either choose to play heads all the time, tails all the time, or in fact, he could flip a coin in the sense that he could randomize between heads and tails, and that would give him the same expected payoff as well. So, in order for Rho to have an incentive to randomize over his strategies, he needs to be indifferent between the two. If he is not indifferent, he's going to play one or the other all the time, so it won't be random. If he is indifferent, then he doesn't care. It gives him the same average payoff. This equality here happens only when p is equal to 0.5 or 1 over 2. You can solve for p yourselves and you will find that p is equal to 1 over 2. So if Colin plays heads with a probability p equals to 50%, then Rho is indifferent between always heads, always tails, or randomizing. If it's another probability, if for instance Colin plays heads more often, more than 50% of the time, then you will be in the first case. Then it means that Rho will most of the time win by playing heads, and his expected payoff will be higher if he always plays heads. So, randomization requires the equality of expected payoffs. If the player is not indifferent, he will not randomize. Since we care about randomizing here, then we need to know when players are indifferent between one strategy or the other. So, if Colin plays heads with a probability of 50% and Rho decides to play heads all the time, then Rho will win 50% of the time and lose 50% of the time. If he plays tails all the time, he will lose 50% of the time and win 50% of the time. If he chooses anything in between, like play one of them 30% of the time and playing the other 70% of the time, on average, he will get the same payoff. So, in a mixed strategies Nash equilibrium, Rho's choice of Q, the probability with which he plays heads, is the best response to Cullen's choice of P, and of course, vice versa because it's a Nash equilibrium. Note, by the way, that pure strategies could be seen as a special case of mixed strategies. Probably P could be, for instance, 0 or 1, which means if it's 0, it means never play heads, always play tails. And Q could also be equal to 0 or 1, which means always play tails, never play heads, and vice versa. So you could look at pure strategies as a special case of mixed strategies. Now, let's represent this graphically. The same way in games applications, we represented best responses for each player. Here, we are going to represent the best responses in the form of the probabilities Q and P. So let's look at Rho's best response first. If P is lower than 1/2, which means if Cullen plays heads less than 50% of the time, then from the previous inequalities, we saw that Rho never wants to play heads. He wants to play tails all the time. So he's going to choose his probability of playing heads, Q, equal to 0. So now P is on the y-axis. When P is lower than 1/2, we are in this vertical area here. When P is lower than 1/2, then Rho wants to set Q is equal to 0 because he wants to play tails all the time to win more often. So that's why we have this vertical blue line. Now, if P is bigger than 1/2, then the inequality is reversed. Rho wants to play heads all the time. So he's going to choose Q is equal to 1. Whenever we go beyond 1/2 and all the way to 1, then Q will be equal to 1. When P is less than 1/2, it doesn't mean Cullen plays heads. It means Cullen plays heads less often than he plays tails. For instance, 25% of the time he plays heads, and 75% of the time he plays tails. Finally, if P is exactly equal to 1/2, we saw that Rho was indifferent. If he is indifferent, then whether he plays tails for sure, or heads for sure, or anything with some probabilities, then it doesn't matter. So since he is indifferent, any Q will do. Any Q between 0 and 1. Q is not less than 0. I don't know what you mean. Q is not less than 0 here. It's between 0 and 1. Now, I can do the same for Cullen. So I have Rho that already depicted. Now, let's move on to Cullen. So Cullen is going to react to different Qs. If Q is lower than 1/2, which means we are in this range here, then Rho wants to play heads with a probability equal to 1. Because if, Cullen, if Rho plays heads less than 50% of the time, Cullen wants to play heads all the time because he's going to win more often. So in this range, when Q is lower than 1/2, colon is going to choose P is equal to 1. It's going to play tails with a probability of 100%. If Q is, on the other hand, bigger than 1/2, it means rho, is playing heads more often than 50% of the time. So in this case, colon wants to play the opposite. Colon wants to play tails all the time. Because remember, colon wins when he doesn't match the penny of the opponent. So, when Q is bigger than 1/2, colon wants to play tails with a probability of 100%, or it is the same as he wants to play heads with a probability of 0%. And so this horizontal red line here means that he never plays heads if Q is bigger than 1/2. And when Q is exactly equal to 1/2, we saw that colon is indifferent between always play heads, always playing tails, or playing a randomization of both. So, in this case, exactly at 1/2, any P between 0 and 1, 0 and 1 being included, will do. Because on average, the expected payoff of colon is exactly the same. Now, we get this weird, like, not weird, but it reminds us of the darkest times of human history. But sometimes this is how best responses will look like. Again, if Q is bigger than 1/2, colon wants to play tails all the time. So he never wants to play heads. So the probability of playing heads should be set to 0, because he always plays tails. The Nash equilibrium will be where best responses cross, the same way we saw that in games applications. So the Nash equilibrium, or Nash equilibria, if they are more than one, are located at the intersection of the best response functions. When P star is equal to 1/2, and when Q star is equal to 1/2. If you want to write down the Nash equilibrium, now you're going to have to write the strategy of rho is to play 1/2 of the time heads, 1/2 of the time tails. And the strategy of colon is to play 1/2 of the time heads, 1/2 of the time tails. So it is a bit more complicated to write the Nash equilibrium, but again, you want to list strategies. You do not want to list payoffs. The strategy now is a mixed strategy, so you want to list what each player is going to play with what probability. Couple of remarks. In constant sum games, keeping your opponent indifferent means that he or she cannot recognize and exploit systematic patterns in your behavior. If you play randomly, your opponent cannot guess what you're going to play next. If your opponent expects you to play scissors most of the time when you play rock, paper, scissors, then he is going to respond with rock more often, because he's going to win more often. Now, you could apply the reasoning that says, if I play scissors most of the time, he's going to play rock most of the time. If he plays rock most of the time, I should answer, my best response would be to play the leaf, paper, most of the time. But then the opponent is going to think, if I play rock most of the time, he's going to play paper most of the time, so I should play scissors most of the time. And vice versa, and back and forth. And you can see that there is never a mutual best response in pure strategies. If one of them plays scissors most of the time or all the time, the other wants to play rock. That's the best response. But scissors is not the best response to rock. So if you go back to the other player who was playing scissors, then he regrets playing scissors and he wishes he could play paper instead. But if he plays paper, then the other opponent doesn't want to play rock anymore. Now he wants to play scissors, and so on. By changing the way you play, you will be able to keep your opponent guessing. That's the idea. And keeping your opponent indifferent is equivalent to keeping yourself indifferent. You can apply the same principle to non-constant sum games, where players' interests are not totally opposed to each other. You could also apply that to something like a coordination game. If you remember the game from 2 weeks ago with Rosia and Tom, who have to decide on a cafe to meet. Instead of saying, I'm going to go there and maybe I'm going to meet him or her or not, they could say, well, if we have to meet every day for a week and we have no way to contact each other, then I can play 50% of the time I can go to one place and 50% of the time I can go to the other. On average, the expected payoff will be the same, so both players will be indifferent. Any questions? Okay, well, let's move on to another example then, the chicken game. Many action movies feature a scene where the protagonist and the villain face each other in a car eventually and they are about to drive into each other. You probably have seen one of the Fast and Furious movies out of, how many do they have? 9, maybe 10 if you count the Tokyo Drift one. And the idea is that they can either go straight or swerve. They can face each other, or they can just go straight, or in the last moment, turn on the side. There are many other action movies that feature this kind of face-off. The game originally was made famous in the 1955 James Dean movie Rebel Without a Cause, where Dean was not really opposing his opponent face to face, but rather he was driving towards a cliff with his opponent on the other side. Well, next to him. So the first one to jump out before the car went over was the chicken. The idea was to just literally get out of the car. If you get first, then you lose face in front of the crowd, and so you're the loser of the game. You're the chicken. It is similar to two cars facing each other. You know, you could just go straight, as in, I have guts, I'm going to go all the way. Or, I'm going to swerve because I don't want to be paralyzed, I don't want to get into a car accident, and so on. In fact, in the mid-1960s, the chicken game was used as an analogy to the nuclear arms race between the US and the USSR. It was used as in, who's the chicken, so who is not going to use the nuclear weapon and who is going to go for it. If both use the nuclear weapon, then they are going to destroy each other the same way two cars could crash into each other if they don't swerve. Then one could go straight, so one could use the nuclear weapon and the other could not. In this case, the chicken, the one who does not use the nuclear weapon, well, is going to experience a highly negative payoff. And vice versa. So I don't want to talk about James Dean because he's not really from my generation, but rather I'm going to use some Fast and Furious analogy. Dom and Brian drive toward each other at a high rate of speed. The driver that swerves first is deemed a chicken and loses face with the rest of the crowd. It is, in some sense, a coordination game. But in this coordination game, they do not want to meet. If they meet, car crash, accident, and all the negative payoffs that come with it. So here, players want to avoid actions with the same labels. So they actually want to avoid coordinating on the same action. They want to coordinate on each doing something different. Let's look at the payoffs. If Brian and Dom both swerve, then it's a tie. They're both chickens. They both go on the side. They don't crash into each other, and they get a payoff of 0. If Dom swerves, but Brian doesn't, then Dom is going to be the chicken. So his payoff will be -1, while Brian is going to be the winner, and his payoff will be 1. We can do the same for the opposite. If Dom is the one who doesn't swerve, but Brian swerves, then Dom is going to get a payoff of 1 because he wins. He's the one with the guts. And Brian will be the chicken, so his payoff will be -1. Finally, both could not swerve. They drive into each other, they crash with all the negative payoffs that come with it, and so their payoffs will be -4, -4. Now, if you do the cell-by-cell inspection, you will find 2 Nash equilibria in pure strategies. The first one is where Dom swerves and Brian doesn't swerve. The other one is where Dom doesn't swerve and Brian swerves. So those 2 cells will be the ones with underlined payoffs. Think about it. If Brian doesn't swerve, then Dom wants to swerve to avoid the accident. And if Dom decides to swerve, then Brian knows that he can go straight and win the game. So swerving is the best response to not swerving. The same way, not swerving is the best response to swerving. Which is how we get those 2 Nash equilibria in pure strategies. Now, in the mixed strategy Nash equilibrium, we are going to go over it. The probability of swerving for Brian and the probability of swerving for Dom will both equal 3/4. Given these probabilities, it is still possible that they get into each other. After all, there is always a chance that they both decide not to swerve. It is just a result of the randomization process. So the probability of a crash happens if they both don't swerve, which will happen with a probability of 1 minus Q star times 1 minus P star. This probability is equal to 1/4 times 1/4, or 1/16. So if they play this game 16 times with these strategies, they are expected to crash once. But again, expected. It is always possible that they end up crashing more times than that. So let's go over the procedure. Again, let's compute the player's expected payoffs. For Dom, it's going to be, with the probability P, it's going to be 0. And with the probability 1 minus P, it's going to be -1. 0 minus 1 times 1 minus P gives you P minus 1. If Dom doesn't swerve, then with probability P, he gets a 1. And with probability 1 minus P, he gets a minus 4. So 1 times P plus or minus 4 times 1 minus P. That yields 5P minus 4. Sorry. Yeah. 5P minus 4. Now, from Brian's perspective, if he swerves, with probability Q he gets 0, and with probability 1 minus Q he gets minus 1. So, his expected payoff will be Q minus 1 if he decides to swerve. If he decides not to swerve, with probability Q he gets 1, and with probability 1 minus Q he gets minus 4, which yields 5Q minus 4. Somebody asked in the chat, what would be the notation of Dom's expected payoff? Is it the total cost of swerving? What do you mean by notation of Dom's expected payoff? This is the expected payoff if he decides to swerve. But I'm not sure why you talk about the total cost of swerving. This is the payoff. This is the utility. This is the expected utility if he decides to swerve when Brian swerves with probability P and doesn't swerve with probability 1 minus P. Expected payoff is the average payoff you will get if you play sufficiently many times. So if you play this game sufficiently many times and you swerve every time, or Dom swerves every time, but Brian plays with probability P and 1 minus P, then the average payoff, when you add them up overall, will be equal to P minus 1. This is the same as an expectation for a random variable in statistics. And we will also go over the concept of expected utility once we finish with game theory. So, the expected payoff is not the payoff he will actually get. This is the payoff he can expect. It is an average payoff between the swerving and the not swerving from Brian. So, in reality, what is going to happen if they play once is either they sell, or they sell, or they sell, or they sell. But if they play many times, you can compute the average payoff. Sometimes it's going to be a 0, sometimes it's going to be a minus 1 if he swerves. If he doesn't swerve, sometimes it's going to be a 1, sometimes it's going to be a minus 4. So, we can graph the best responses the exact same way as before. Let's start with Dom. So, if P is lower than 3/4, then Dom wants to swerve all the time. So he wants to set Q is equal to 1. So locate P equals 3/4 here. And when P is higher than this, so when P is between 3/4 and 1, lower than 3/4, my bad. So this range. Then Dom wants to swerve all the time. So he wants to play swerve with a probability equal to 1, which is why we have this vertical blue line here. If, on the other hand, P is bigger than 3/4, now Dom wants to not swerve, doesn't want to swerve every time. Or never wants to swerve, sorry. So Q will be 0. And if P is exactly equal to 3/4, then he is going to be indifferent and he is going to, any probability will do. The 3/4 is the probability that makes Dom indifferent between swerving and not swerving. The same way we found 1/2 with the matching pennies game. So once you have these payoffs, make them equal and find the probability that makes them equal, and you will find 3/4. We can do the same for Brian. If Q is lower than 3/4, so this range, then Brian wants to swerve all the time. So he wants to set P is equal to 1. If Q is bigger than 3/4 in this range, then he wants to, he never wants to swerve. He always wants to go straight, because on average he will win more often. If Q is exactly equal to 3/4, then Brian is indifferent between swerving and not swerving, and any probability here will do. Note that now the best response functions cross at 3 different locations. And these are all the Nash equilibria we have here. The Nash equilibria are located at the intersection of the best response functions. So the first one is where Q is equal to 1 and P is equal to 0. That's a pure strategies Nash equilibrium. It is one of the cells we saw before. It is the case where Dom swerves with probability 1. So this is the case where Dom swerves and Brian doesn't swerve. The other pure strategies Nash equilibrium is where Dom doesn't swerve and Brian swerves. This will be this point here. And you can see that these points are located on the axis. On the axis, it means that either Q or P is equal to 0. Here, P is 0, Q is 1. Here, P is 1, Q is 0. And the third one is if they swerve 75% of the time each, then they are indifferent to each other's actions. And so this is the mixed strategy Nash equilibrium here. What's powerful about this graph is that it shows you not only the pure strategies Nash equilibria, but also the mixed strategies ones. There could be more. So this graph summarizes the whole exercise. If I ask you find all the Nash equilibria in a game, you will have to find the Nash equilibria in pure strategies and in mixed strategies. If I am more precise, if I say what are the pure strategies Nash equilibria, then only go for the pure strategies Nash equilibria. This graph, although not being super easy to make at the beginning, once you get a habit of it, it helps you double check your results. The Nash equilibria in pure strategies are in this graph because these are best responses. And as part of the best responses, we have the best responses, the pure strategies best responses. The case where Q is equal to 0 or P is equal to 0 are pure strategies, and they are also best responses. So wherever the best responses meet, that will give you the Nash equilibria. So it's a very good graph to double check your results. If your graph doesn't cross as many times as the number of Nash equilibria you found, then you're wrong in either. Either your graph is wrong or your Nash equilibria are wrong. So the 3 Nash equilibria formally should be written swerve, don't swerve. That's the first one. When Q star is equal to 1, P star is equal to 0. The second one is where Q star is equal to 1. So Dom doesn't swerve, but Brian swerves. And the last one is a bit more wordy. 3/4 serve, 1/4 don't swerve. So 75% of the time swerve, 25% of the time don't swerve. And for Brian, 75% of the time swerve, and 25% of the time don't swerve. Note that you are required to write the Nash equilibria correctly if you want to get full marks in exams. This is one way to write it correctly. Another way could be in the mixed strategy Nash equilibrium. Dom swerves 75% of the time and doesn't swerve 25% of the time, whereas Brian swerves 75% of the time and doesn't swerve 25% of the time. So a lengthy sentence could also do the trick. But make sure that you know how to express them. So, in words, if Brian swerves with a probability of 3/4, Dom is indifferent between swerving and not swerving, or any randomization of both. So anything is the best response for Dom at this stage. Now, anything including swerving with a probability of 3/4. So if Dom randomizes his actions this way, then Brian becomes indifferent to Dom, and Brian could also randomize. But it is only when they precisely randomize this way, 3/4, that they make each other indifferent. If Brian randomizes 50-50, then Dom doesn't want to randomize. He wants to play one strategy over the other for certain. When he plays 75% of the time, Dom doesn't care. He could play anything or any randomization of both strategies. But if he randomizes 50-50, then Brian randomizing 75-25 is not a best response anymore. If Dom randomizes 50-50, then Brian will prefer to play either swerve or not swerve. It's only when they randomize exactly this way, 3/4, 1/4, 3/4, 1/4, then that they are indifferent to each other. So this will be the only moment they play a best response to each other. The only moment where they randomize and they randomize as a best response to each other. So somebody asked in the chat, if the graph is linear, it means Dom is indifferent. What do you mean by linear? A straight line? Horizontal line? Vertical line? I'm not sure what you mean by linear here. Straight line is not the same as horizontal line, but if you mean horizontal line, yes, this is the stage where, in this case, Dom is indifferent. So any probability of 0, probability of 1, or probability of 50-50, or probability of 3/4, 1/4, or probability of 2/3, 1/3, or probability of 25, or 1/4, 3/4, same expected payoff. You can actually just try this. Just plug numbers. You will see that the expected payoff of Dom is the same when Brian swerves with a probability of 3/4. Okay, let's take a break here. It's 12:30. Let's resume at 12:40. This week, we are going to talk about part 4 of game theory, which consists in looking at mixed strategies. The usual disclaimer: probability player vertical blue line. It means James is not swerving very often. It means he's going straight pretty often. Since he's going at his expected payoff. His payoff is P, so 1 times P, plus 1/2 of column the only reason why you the other. The idea is that every time precises. If I am row and I play heads, but column plays tails, I lose. I get -1. And so I'll be like, shoot, I regret my choice. I wish I had played tails instead. And so heads was not the best response to tails. Okay? It's a good way to check your results. It's a good way to double check your results. It's easier for you guys to get partial marks if you put something like sometimes it's going to look like this. And remember to don't forget to write to show the whole best response. Or if you dynamic games. So instead of playing at the same time as your opponent, what happens if you play before your Okay, so we went over two different games in this lecture. We went over matching pennies, where we saw that there are no pure strategies Nash equilibrium. The only Nash equilibrium we found was in mixed strategies. Then we moved on to the chicken game that had both a Nash equilibrium in mixed strategies and two Nash equilibria in pure strategies. Those are different Nash equilibria. Somebody in the chat asked if mixed strategy Nash equilibria are as good as pure strategies Nash equilibrium. A Nash equilibrium is a Nash equilibrium, whether it's mixed strategies or pure strategies. Or it could be sub-game perfect equilibrium. That's something we're going to see next week. Or it could be stable equilibrium, or it could be sequential equilibrium, and so on. Some of them have different characteristics, which are sometimes preferable. In a case like that, mixed strategies are just interesting to look at because they help us predict what people are going to play, in particular in games of pure conflict. So if you know that there is, for example, you play matching pennies, you can expect that your opponent is not going to play heads all the time or tails all the time. Same as rock, paper, scissors. Now, this Nash equilibrium is more interesting when you play the game many times in a row, because you want to keep the opponent guessing. And it also makes less sense to look at a mixed strategy Nash equilibrium when you play the game once. Let's say play rock, paper, scissors with one of you guys. Once. Just, winner gets something and loser loses something. Well, how do you know if me playing paper is a result of me deciding to actually play paper, or me me flipping a coin or something to decide whether I should play rock, paper, or scissors? So it's kind of confusing. It's not super clear whether, when you play the game once, whether your decision comes from a randomization process, or if you decided to go for paper in the first place, like with a probability 100%. When you play the game repeatedly, then mixed strategies get more interesting, because since this is a repetition of the same game, you can just see over time and look at your strategy profile over time as maybe an approximation of a mixed strategy. The same way, when you flip a coin once, you could say before flipping the coin, I have a certain probability of getting heads or tails. But if you don't know if the coin is weighted or not, if you don't know exactly the probability of getting heads or tails, because the coin could be a weighted coin, and it gives you a higher probability of getting heads, for instance. Let's say you flip once and you get heads. Well, you don't know right now if the probability of getting heads was 50% or if it was 60 or 70% because the coin was weighted. You need to repeat the experiment many times, and let's say you flip a coin 1,000 times, then the law of large numbers is going to kick in. And if you got around 600 heads for 400 tails around, then you might guess, by that time I should be close to 500 for each. If I am closer to 600, then probably the coin is weighted. So mixed strategies make more sense when you are repeating a game many times. Okay, we don't have much content to cover left, but I want to give you the general procedure about how to solve and how to find the mixed strategies Nash equilibria. So let's go back to matching pennies and let's do the whole process, but the formal process that we, the TAs and myself, expect you to reproduce in exams. So first, you start by assigning a probability of playing an action next to each player. If you want, you can use the same color. It's just a way to not get lost. It's just a personal recommendation. If you don't feel like it, feel free not to do it. So, For colon, I call the probability P, and for P for heads, tails, and 1 minus P for tails. You could swap them. You could say, let P be the probability of playing tails. It doesn't matter. What matters is that the sum of the probabilities, P and 1 minus P, is equal to 1. The same way, Q plus 1 minus Q is equal to 1. If you have a randomization over 3 strategies, then you would say, for instance, P1 for strategy 1, P2 for strategy 2, and 1 minus P1 minus P2 for strategy number 3, because they have to add up to 1. Typical example, rock, paper, scissors. You do not randomize between just paper and scissors, or just rock and paper. You're going to randomize over the 3 different characteristics, over the 3 different strategies. So you're going to have a probability P1 of playing rock, P2 of playing scissors, and the complement 1 minus P1 minus P2 of playing paper. Now, once you do this, you're going to start by saying, start with assume colon plays heads with probability P. I'm reading something in the chat. So same QI, Q2, and 1 minus Q1 minus Q2 for the other player. Yes. Yes. It's not very clear. Please, guys, try to put in a question mark or something in the questions. I'm easily confused. But yes, if you are also randomizing over 3, 4, even 5 different strategies for the other player, same thing. Choose other probabilities. I call them P and Q. You can call them T and V. You can call them L and M. Why not? Whichever notation you are comfortable with. So, now that I assume that colon plays heads with probability P, then I'm going to look at the best responses of row. If row plays heads, he gets here, with probability P, he gets 1. With probability 1 minus P, he gets minus 1. So his expected payoff is going to be 2P minus 1. If row plays tails, he gets, so now we are looking at the second row. With probability P, he gets minus 1, P times minus 1. And with probability 1 minus P, he gets 1, 1 minus 2P. I recommend you to also detail this computation. It's not going to be for partial marks, but it's going to be easier to find the expected payoff. Very often, I find, and personally and in other students' exams, that students make a mistake in signs, and that's the case for other classes. They put a minus instead of a plus, or things like that. Well, by detailing the whole computation, maybe you can make sure that you're not making any sign error. In particular, because in cases like that, it looks very symmetric. 2P minus 1, 1 minus 2P. But if you go to the chicken game that we just saw previously, the payoffs don't look like that. It's like 1 minus P and then 5P minus 4 or something like that. Okay? Now, once we know the expected payoffs from playing each strategy, make him indifferent. Rho is indifferent between the two actions if 2P minus 1 equals to 1 minus 2P, or if P equals 1 over 2. So when colon plays heads 50% of the time and tails 50% of the time, Rho doesn't care between playing heads all the time, tails all the time, or a randomization of both. Any randomization of both. Now you do the same for colon. Assume row plays heads with probability Q. And then you can find the probability Q that makes colon indifferent between heads, tails, or anything in between. Once you find the probabilities, make sure you report them correctly. Remember that it's not always symmetric. Sometimes one player could be half-half and the other could be 1/4, 3/4. So make sure that you report 1/4, 3/4 on the right player and 1/2 on the right player. Otherwise, you will get the Nash equilibrium backwards, so it will not be correct. Question in the chat, if it is 3/2, then what it means? Again, I don't understand this question. Please be more clear. I don't know what it means. Should you draw the graph in the exam or can we only use the equations? It depends on what I want from you. So I am expecting you to be able to draw the graphs. The method is the same. Don't learn the graphs by heart. There are many other graphs with different shapes. You can go over them online. There's a plenty. So don't learn them by heart. Just go through the best responses every time and learn how to report them. I might ask you, show me the Nash equilibria on a graph, which includes showing me the pure strategies Nash equilibria. Or I might just say, find the mixed strategies Nash equilibrium or find the Nash equilibria, in which case you're free to use either method. But again, show your process if you want to get partial marks, but you're wrong. If you just put 1/2, for instance, for matching pennies, you probably won't get full marks. Especially for mixed strategies, we expect you to show us your process. So what I'm showing you here, this thing, is exactly what I want you to report. And the tutorial, the problem set, the answers will also show the exact same process. It is literally the process I learned with back then, many years ago. And to me, this is the most consistent problem, the most consistent way. I've seen many other ways to do it. This is the most consistent. It is hard to make a mistake when you do it this way, as opposed to using words. I've seen questions which are like, or I've seen solutions where you have to report the whole thing. You say, oh, you play heads more often than not, and so on and so forth. If you start being wordy, it could be confusing for you. You could make typos, say heads instead of tails, and so on. And it could be confusing for the reader, for us, for the TAs and myself. So my advice is just make bullet points, heads, tails, indifferent. The other one, same thing. If column plays heads, boom. If column plays tails, boom. Is indifferent if, boom. And that's it. If the equations are too complex, no, because the equations, once you solve them, once you find the probabilities, like this one, then you're ready for the graph. The graph just says more than half, less than half, or exactly a half. So it will not be too complicated. Now there's another question which has been reformulated. So like probability of 1/2, what if in that place, if the probability, okay, try to also be more correct in terms of grammar. It's pretty hard to understand, but my understanding is, what do you mean, what happens if we find the probability of 3/2, which is bigger than 1, or if we find a negative probability? After all, this is just an equation. Well, if the probabilities you find are beyond 1 or below 0, then it means that there is no way, it's not possible to mix, in the sense that the player never wants to mix between those two strategies in this case. He will always prefer to do one over the other. It means that one inequality will always prevail. That actually could be a way to check that the player doesn't want to mix between this strategy and that strategy. If you cannot solve the equation, then there cannot be a mix between those two. But there could be a mix between 2 other ones or 3 other ones. I could make the game arbitrarily complicated and make you solve equations for hours. Obviously, that's not my objective, but you should be able to understand how this can be extended to many more strategies, at least to 3 strategies. I could ask you to solve rock, paper, scissors, for instance. Now, If you cannot solve one or both of the equations, for instance, you get a negative value or a value bigger than 1 for a probability, it means that one player cannot be indifferent between both actions. So that players won't mix in a Nash equilibrium. In fact, try this on a prisoner's dilemma and tell me what you find. You will find a negative probability or a bigger than 1 probability. Why? Because in the prisoner's dilemma, players always prefer to confess strictly, because confess strictly dominates not confess. So the player is never indifferent between confess and not confess. He always wants to play confess. Makes a higher payoff. So in this case, the math will not give you a probability between 0 and 1. Yeah. In fact, you could make the same graph as here for the prisoner's dilemma. But instead of having kinks, you will have two straight lines, and they will meet only at the probability of playing confess is exactly equal to 1. That would be the only Nash equilibrium. No mixed strategies Nash equilibrium in the case of the prisoner's dilemma. So the main takeaways of mixed strategies. First of all, it can be a best response to play a strategy involving actions played with some probability. But that requires indifference between two strategies. In particular, in the games of pure conflict, matching pennies being one of them, a player's win means a player's loss. So you do not want to be predictable. Otherwise, you're going to lose more often than not. If an action is strictly dominated by another action, there is no Nash equilibrium where the dominated action is played with some positive probability. Again, the player cannot be indifferent between two strategies if one strategy strictly dominates the other. In a Nash equilibrium in mixed strategies, expected payoffs are equalized so that randomization is a best response. One more thing, very important result. There is always at least one Nash equilibrium. I could give you the weirdest game ever. There is going to be at least one Nash equilibrium. It could be one in pure strategies, like the prisoner's dilemma, or one in mixed strategies, like matching pennies. Or they could be more. One more thing I want to add. The total number of Nash equilibria in a game will always be odd. If I ask you to find all the Nash equilibria in a game like, for instance, the chicken game, and you find two pure Nash equilibria, then you can already expect that there should be one mixed strategies Nash equilibrium. It's either 1 or 3 or 5 and so on. This is actually called the index theorem. So there is a whole mathematical proof. You can check it online. It's pretty involved, I believe, and it's very mathematical. It consists in counting the number of Nash equilibria and so on. If you find 0 Nash equilibrium in pure strategies, then there must be at least 1 in mixed strategies. And if it's not 1, it's going to be 3, because in total there must be an odd number. If you find 1 Nash equilibrium in pure strategies, then chances are there will not be a mixed strategy Nash equilibrium. And if you find 2, 3, 4, maybe 5 Nash equilibria in pure strategies, expect to have as many mixed strategies Nash equilibria as you need to make the overall number of Nash equilibria odd. Just a tip. It's a good way to check your results in the exam. So we expect you to be able to produce those graphs, and don't forget that those graphs will also report the pure Strategy Nash equilibria. So if we ask you to draw the graph, look at it as a way to make sure you get marks in the exam. Because once you get the graph, if the graph doesn't coincide with the Nash equilibria you found, then there is a mistake somewhere and you can fix that mistake. So look at it as not as an annoying question in an exam, but rather as a way to double check that all the Nash equilibria you found before are correct. If everything matches, at least you know that that exercise will give you full marks. Always look at the bright side, right? Any questions? Oh, I see one. What is the difference between probability of 2/4 and probability of 3/4 on the decisions made by the players? So 2/4 is equal to 1/2. What is the difference? Well, the difference is that one probability might make the other player indifferent, but the other probability will not make him indifferent. This is what we have here. If P is exactly 3/4, oops, here, then the player is indifferent. But if it's bigger than 3/4, like 0.9, then the player is not indifferent anymore and he wants to play one strategy all the time. If the probability is lower than 3/4, like 1/2, then he wants to play the other strategy all the time, because on average, his payoff will be higher. All these best responses come from comparing payoffs. They come from comparing P-1 and 5P-4. One is bigger than the other when P is lower than 3/4, and vice versa. Any other questions? So, just to bounce back on this question, if in this game, for instance, here, if one player plays swerve with a probability of 3/4 and not swerve with a probability of 1/4, but, well, if he does that, the other player is indifferent. So if the other player is indifferent, he could play one, the other, half-half, 3/4, 1/4, 1/3, 2/3, doesn't matter. The expected payoff will be the same. You can check that mathematically. So, the other player could choose either, but if the other player chooses something else than 3/4, 1/4, like he chooses to randomize 1/2, 1/2, 50-50, then the first player, who was playing 3/4, 1/4, is not playing a best response anymore. Because in turn, when the second player plays half-half, then the first player now wants to play an action for sure. He wants to play one strategy or the other for sure. So that's why when you look at Nash equilibria, it's always important to go one way and backwards. If I play this, your best response is to play that. But if you play that, is what I'm playing right now a best response? If it is, I have a Nash equilibrium. If it's not, I do not have a Nash equilibrium. I only have a one-way best response. For Nash equilibria, it always goes two ways. I play best response to you, you play best response to me at the same time. That's it for this lecture on mixed strategies. Have a good rest of your week and see you in the next one. Bye.